Okay, so for Friday, I'm gonna give y'all an option. Um, this page didn't load yesterday, so whenever I gave it to you guys, if you actually tried to do it, it did not show up. Yeah, it basically said was like you cannot do this. It was a bad or corrupted file, so it's up there now and it should be working. I can try to go through a couple of these if you want to, or I can just come up with my own examples and you can use these for practice. That's your choice. Which one would you want? Come up with my own examples? Okay. Because then you can just do these for practice. And if you can always ask and double check. So like anytime at any particular point in time when we're going through this, if you guys have done the homework and you have questions on it, you can come back and just ask it and I'll answer it for you guys. I'm not going to be like, no, answer it on your own because that would be kind of dumb because that's the whole point of the practice so that we can go over it. I will tell you guys that there are a couple of ones down here. So, like the first one's with the grid. I'm not too terribly worried about you guys because it's just plotting and making a line. It's not too big of a deal. But these word problems down here on the second page, these are going to involve two dimensions, which is what I'm going to try to work on today as a couple of examples for you guys. So that you can actually have some examples to work with. So I'm going to switch on over to, let's see, what is that? Kinematics. And we'll put it in velocity this time. So I think the big deal that's going to start happening on this one is that positions and velocities, they do not have to be in just one dimension. So if you have a velocity that's in two dimensions, so a one-dimensional motion would be like straight up and down. That's one dimension. Okay, or straight left and right. So if you think like an old game controller would be a good example of like one-dimensional motion. You can either move left or right, or you can move up and down. But if you have something that is not in one-dimensional motion, I anything that is not one-dimensional can be broken down into one-dimensional components. So if something is diagonal, it automatically has a slope that goes along with it. And if it automatically has a slope, that means that it has a rise over run, which means that it has an x component and it has a y component. And any diagonal line that we could possibly humanly draw should be able to be broken down into an x component and a y component. Um, we call these vectors. So yesterday I gave an example where there was a person here at point A, and there was another person kind of over here at point B, and I did not make it a straight line to go from one person to the next. And if we're trying to measure that distance between person A and person B, in order to gather that distance to make sense in an algebraic sense, we would need to take this vector and we would need to break it down into components. So since this is a displacement vector, we can either call this d or x. I prefer to call it d because, d stands for distance. But if you see the letter x, that can also stand for a distance, just like it does in the xy coordinate plane. So what we can do is we can just break these down into components and measure those values. And I'm going to make up some numbers. So if y'all are like, well, wait, how did I get that? I'm just making it up. If this is 5 units, and let's just put meters because we normally use the KMS system. And let's say that this one is 7 meters. Okay. And then you have to use the Pythagorean theorem to find out what the third side is. So in order to find the displacement of this vector, we're going to have to use a squared plus b squared equals c squared. And the two sides, it doesn't matter which one you make x and which one you make y. It really doesn't matter. So this is one leg, this is another leg, and this one makes the hypotenuse. Okay. So if we go 5 squared plus 7 squared equals c squared, that comes out with c being equal to the square root of 25 plus 49, which is math. Comes out to be 74. Okay, I believe you. If you look at the dimensions also work because you've got meters squared and then you take the square root of it, and that comes out to meters. So even using the Pythagorean theorem is actually dimensionally correct. Okay, which is probably something that y'all haven't thought of before. Be like, I wonder, is the Pythagorean theorem dimensionally correct? Normally in geometry, they just give you numbers. Yep. No, so like, yeah, when it comes to sig figs and AP Physics, there are not a lot of rules in terms of that. Like if you take pre-AP Chemistry and AP Chemistry, sig figs are absolutely huge. In AP Physics, you don't really have to worry too much about sig figs. I would say round to the nearest tenths place, and you'll be okay. So if that's really like, is that 74 point what? Oh, so wait, oh, thank you. So like c squared is 74. So when we take the square root of it, it comes out to what? 8.6? Like this? Okay, so sorry, that should be meters squared then. So 74 meters squared is equal to c squared. So when we take the square root of it, that comes out to 8.6 meters. And that's going to be the displacement from point A to point B if you've got something that's in two dimensions. Okay. Now, another thing that's going to be really important to us is to be able to find out the angle at which this vector is pointed. So if you're pointing from A to B, what we normally do is the up and down direction. Up would be north, down would be south, to the right would be east, and to the left would be west. Okay? So in these cases, when we're talking about vectors and the directions that they go, up would be north, down would be south, right would be east, left would be west. In this case, we have something that is going up and east. So we're going to call that, it depends on whether or not our angle is going to be 45 degrees or not. It looks like since we have a larger number up here, it looks like the angle is going to be greater than 45 degrees. Okay, so there's a couple of things that we can do. SOHCAHTOA is probably going to be the easiest way to do it. So, so yeah, we got to get our SOHCAHTOA going. You haven't done SOHCAHTOA? Oh no. Well, that's okay. It's really not that bad. Uh, we'll do a quick little trainer refresher course. Anytime you're dealing with a right triangle, and this is an important part, the triangle has to be a 90-degree triangle. Otherwise, SOHCAHTOA does not work. Fortunately, in AP Physics, everything diagonal can be broken down into a right triangle. If it's vertical, you don't need to worry about it. If it's horizontal, you don't need to worry about it. If there's an angle, we can turn it into a right angle. Okay, so what we're going to do is if this is the angle on this side, which I'm going to call the letter theta, then this is going to be the opposite side. The hypotenuse is written as h, and the adjacent side is the side that's touching the angle. Okay, SOHCAHTOA is just a ratio. It's a fraction that tells you a ratio of the length of the sides to each other. There are three special ratios: the sine, the cosine, and the tangent. The SO is where the sine comes in. So if you have the sine of an angle, that's equal to the opposite over the hypotenuse. So I think we don't have the hypotenuse, but we do have the opposite side. Oh wait, we do have the hypotenuse. It's 8.6. Um, I don't really care which side you use. So any of these, since we have all three sides, any of these would work out just fine. Um, However, if you're doing this from a professional standpoint, you should only use the sides that you measured and knew. So in professional work, you should never use 8.6 because you calculated 8.6. You didn't physically measure 8.6. So if you want to do this like the professional way, you're going to use the tangent, which would be the opposite over the adjacent. Even in AP Physics, though, I don't care which side you use because it should come out to the same answer either way. But there's a reason why they use the tangent, and it's usually because you measured those physically, so you know those numbers exist. If you messed up on the 8.6, the angle is going to mess up too. but since you knew you measured those, you can actually have a less chance of getting compounding errors to occur. So I'm gonna do it the high school way, and I'm gonna say, you know what? I have the opposite, and I have the hypotenuse, so I'll just use the sine since we're talking about it right now, and I'll say that the sine of my angle is equal to the opposite side, which would be 7 meters, over the hypotenuse, which would be 8.6 meters. And a couple of things happen that you don't necessarily even talk about in math class. One, the meters cancel out, which means that you really are just looking at a number. It's really a ratio. So the meters do end up canceling. And the way that Mr. Broadway does it is I type in 7 divided by 8.6 and get a decimal. And then after that, I take the inverse sine of both sides. So I'll get the sine of theta equals something, and then I take the inverse sine of that something. Okay? So first of all, what's 7 divided by 8.6? Y'all got the calculators. Point 813. Yeah, and you can literally just throw this all in the calculator at the same time, and that's fine too. In the calculator, you're looking for the button that says sine to the negative 1 of 0.813. And you have to make sure that your calculator is in degree mode. For the TIs, any of them, that's the math button. And then there will be a sign that says DEG and RAD. We don't want radians. We want degrees. Degrees are what we use for most of the time. So if you have to put your calculator in a mode, 9 times out of 10, degrees is going to be the way to go. So if you type in your calculator sine to the negative 1 or inverse sine of 0.813, it comes out to what angle? 54.3 degrees? Okay. So that means that if we were to try to say this, we need to give it a magnitude and a direction. So our displacement is going to be 8.6 meters at 54.3 degrees north of east. Okay? Because what you did is you started at east and you moved that angle up. Okay? If you said 54.3 degrees east of north, that means that you would be starting at north and you're moving the angle more towards the east. So that's why whenever we think about northeast, that's why they say north first and then east. They don't say east north. Okay? Right? So like northeast, southwest, northwest, southwest. We always like whenever we talk about it in the English language, we normally base everything off of the east and west sides, and then we move the pitch up and down. So we think east and west first, and then we think, oh, well, that's 23 degrees this way, which kind of makes sense. I mean, you could actually think about it the other way and have everything based off of up and down, and then be like, oh, it's 23 degrees this way. Neither way is wrong, and if you want to write it the other way, you just have to use the complement of this angle. So if you wanted to use east of north, it'd be whatever the heck 90 minus 54.3 is. Either way would be correct. Yeah, that works. Okay, I don't care whichever way you write it, but I I'm normally gonna write it like this. Okay, and I can easily find the complement. It's not that big of a deal. It really doesn't bother me. Okay, so there are a couple of things that we can do dealing with the displacements being in 2 dimensions. Another thing that's important is if you're dealing with velocity, the two velocity positions can be not the same number. Okay, what's a good way to put that? I need to scroll down. Let's see here. Does everybody have this to start with? Okay, so I'm going to scroll down just a little bit. If you're dealing with the velocity vector, so we'll do a classic river problem. So you're on a boat and that boat is traveling across the river, but the river itself has a current that goes along with it of 2 meters per second, which is a pretty fast current. So if you're over here and you try to cross the river, and you start rowing straight across, are you going to go straight across? No, it's going to go more like this. Okay, so let's say that you have a row speed and you can row at, let's say you're super beefcake and you can do like 5 meters per second. That's rowing at 10 miles per hour. That's pretty good. It's like beast mode. So what we can do is your speed or your velocity, I should say velocity, sorry. Your velocity is not 5 meters per second, and your velocity is not 2 meters per second. What you're doing is you're actually kind of going this way a little bit. So your total velocity is the addition of the two velocities put together. So what we can do, if you're adding velocities or adding any vector in two directions, what we can do is just write out the arrow. So I'm going to draw a horizontal line, and I'm going to put 5. And then once you get done with making the horizontal line, at the head of the arrow, you're going to attach the tail of the next one. So if this is 2 meters per second going down, I'm going to attach that tail right here. And I'm going to make it shorter because that is 2 meters per second. And our resultant velocity is going to be the hypotenuse that exists between those two arrows. So if you need to add the velocities together, we can add the velocities by doing the Pythagorean theorem. And once again, I did not make a nice, easy Pythagorean triple. I'm sorry. I'm apparently not very good at that. 5, 6, and 7. Hello. Okay, back to the program. Pythagorean theorem time. Y'all were talking about it was like 29 or something like that. So I'm going to put the units in there because in physics it's important to write the units. So that's going to be 5 meters per second squared, like this, plus 2 meters per second squared equals the resultant squared. And I know people eventually start asking me, they're like, do I have to write the unit down for everything? And the answer is no, you don't. I would start it off until you get comfortable with it, and then after that, you can kind of wean away from it. But if you're just doing this the first couple of times, I would highly recommend writing the units out. Okay, so 5 squared is 25 meters squared per second squared, and the 2 squared is 4 meters squared per second squared. Plus, this gives you a good way to double check. So, like, these units match up, so I can add these together and not go crazy. So, like, 25 plus 4 is 29 meters squared per second squared is equal to c squared. So, when I take the square root, I'm going to get the square root of 29 meters per second. I can pull that out since the square root of meter squared is just a meter, and the square root of second squared is just a second. This also lets me know that this equation is dimensionally accurate because I get speed or a velocity on the other side. So the square root of 29 is a decimal. You can answer, what was it? 5.4. You can answer it in a decimal or a square root, and I do not care. But please make sure you put the speed at the end of it. So this would mean that we are going 5.4 meters per second this way. Well, what is this way? This way is diagonal, so I need to indicate what direction I'm going with an arrow. So since we did the sine last time, why don't we use the cosine or the tangent? Which one do y'all want to do? It doesn't matter to me. Tangent? Okay. Tangent's fun because sometimes tangent can blow up. Um, so like if you get the tangent of 0, I think that's a no, sorry. If you get the tangent of 90 degrees, I think that's a problem. It explodes. So we'll do the tangent. This is the TOA of the SOHCAHTOA. So this is the tangent, and it's equal to, of an angle, it's equal to the opposite over the adjacent. I'll just write ADJ for adjacent. So we don't know the angle, so I'm going to write tangent of theta. The opposite side is 2 meters per second, and the adjacent side is 5 meters per second. And notice that even though these are meters per second, the units are still going to cancel out because it's meters per second on top and meters per second on the bottom. So these go away. So really what we're looking for is we're going to find the inverse tangent, tan negative 1, of 2/5. Sometimes you'll hear teachers call the inverse, this tan to the negative 1, sometimes you'll hear them call it the arctangent, and that, for our extension purposes, means the same thing. Okay, we are basically looking for the angle whose tangent is 2/5. So if you type in your calculator tan to the negative 1 of 2/5, it should give you, theoretically, fingers crossed, a number that goes along with it. 21 degrees-ish. It was 21 point what? 8? Okay, we'll go with that. 21.8 degrees. And it's going south, right? So our velocity is going to be 21.8 degrees south of east, because we're starting at the east direction and we're going 21.8 degrees south of east. Am I going the wrong way? Well, here's east. East is, yeah, east is going this way, right? So I'm going to go 21 degrees south of east. So I think I'm okay. But there are many times when Mr. Broadway is completely and totally wrong. So always double check me and always ask questions because I am not a perfect person. I am far from it. So I am going to make mistakes. They're going to happen. Okay? So here's an example with displacement, and there's also an example with velocity. We can take these numbers and we can add them together, we can subtract them, and that's going to be similar to what's going to be on those word problems on that section. So do you want me to work another one, or are y'all okay with these? Everybody okay? All right. Whenever you work them, if you have questions on them, we can always do those questions after you guys work on them. So don't think that just because you if we've already done it before, I'm going to say, well, just go back and look at the video. But if we haven't done it before, then you're more than welcome to ask, even if it's something that we are kind of far behind on, because we can answer it pretty quick. All right. So there was another one that I gave you, I think, and it was because I gave you two at the same time, and I think the next one dealt with acceleration, right? I think these are going to start having to do with a lot of graphs. So I'm going to start trying to show you the different kinds of graphs that can occur for kinematic graphs. And we're going to kind of deal with acceleration to start with here. So I'm going to go back to our notes, and I'm going to put it on acceleration. So here we go. There are a couple of different ways that you can graph motion. The easiest way that you can graph motion, and the one that y'all are the most familiar with, is the DT graph, which is a distance versus time graph. And what that involves is you take a graph, and it can be positive and negative, but normally there's not a negative time part. So right here at the origin, this is going to be t equals 0. And this normally indicates the very beginning of the event. So basically, if you're starting the timer, that's where t equals 0 is. And we don't normally have a negative x-axis because negative time sounds weird. So like we don't really know how to do negative time. Um, the arrow of time is always positive. We can't actually go backwards because of several different reasons. Logically, spiritually, all of these things. If you could go backwards in time, oof, that'd be really messy. Okay. So we're going to put distance on the y-axis, and you can graph the motion of an object as it goes through distance versus time. And here's a good example of some kinds of motion that you might see. If you have a straight line in any particular direction, this involves some kind of constant speed. So any straight line would mean that you have some kind of constant speed. Even if that speed is zero, so like if you're looking at the flat line up at the top, your speed at that particular location is zero, and that number is not changing. So if it's not changing, I'm going to call that constant. That is a constant speed. And then on the other side, this one is a straight line, or at least straight-ish, so that's also going to be a constant speed too. The constant speed for the one on the left is a positive constant speed because you are covering a positive distance over time. The one in the middle is going to be, well, zero. And then the one on the right side is going to be a negative constant speed because you're covering less distance. It is possible for you to go further past the point where you came from. And if that does happen, then your graph can go into negative territory. And there's nothing wrong with that. That's perfectly fine. Yep. 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 So like this would be like I am moving to one location, work would be a good one. I'm staying here. This is basically like us going to school, right? So like in the first part we travel there, then we stay there, and then we go back there. And this would be if you leave somewhere else after the weekend, you're just like, "All right, time to leave." And then you go somewhere else. Yes. Any questions? Okay. There's a couple of different things that we can get from this graph like mathematically. And the first thing that I want to say is that the slope of the line is equal to the speed. So if you can calculate the slope of the line using rise over run, you can find the speed of the object. Okay? And then the total distance that was traveled, or I probably should say total displacement because it can be negative. The total displacement is equal to the area under the curve. So if we are trying to find the speed of this constant speed, we can find the rise over run by just taking 2 points that we actually know what are, and we can calculate the rise over the run and get the slope of this line, and that would be the speed that it's actually traveling. Okay, or if we wanted to find out the total distance that it was traveling, we can take the entire segment of the time that it actually traveled, and we can find the area. I'm going to try to erase this. There it goes. We can find the area under of this triangle. And usually whenever they do this to us in AP Physics, they make them very, very simple shapes. So it's either going to be a rectangle, a triangle, or if it's not, something that you can approximate very easily by counting squares. They don't want you to get lost in the actual mathematics of it. They want you to see that if I want to try to find out how far that I'm going, I can just calculate the area under this curve of the displacement time graph, and it will tell me how far we're actually making it. Okay? It'll tell me the total distance. Okay? Although I'm actually, now that I think about that, I may have actually been lying to you. So let's find out. Is this dimensionally accurate? Is what I just said dimensionally accurate? Well, let's find out. Okay, what is time measured in? Seconds. Okay, what is distance measured in? Okay, so if I find the area under the curve, let's say that this is 4 and this is 3. Okay, so how would you find the area of this triangle? So that'd be 1/2 um, 4 seconds times 3 meters. Does that come out with meters? Whoops, that doesn't work because that gives us meter seconds, right? That is not a meter. So Mr. Broadway just lied to you. Sorry, sorry, sorry. That's the next chart. My bad. If you were writing that in your notes, scratch them out. Pretend that that doesn't exist. Well, we will do an area under the curve, but it's the next one. Sorry. I told you I'm not a perfect person. I just had to preface that before I like uber messed up. So, but the slope does actually come out to the speed. That is dimensionally accurate because if you calculate the distance and you divide it by the time, rise over run, the rise would be in meters and the run would be in seconds, and that comes out to be meters per second. So the slope of the line totally does work. I was not lying to you about that one. Let's talk about the next graph. The next graph is where we're going to be doing some area stuff. The next graph that we can do is one that's called a velocity time graph. So we'll put velocity here, yeah, and we'll put time down here. And we can do the same thing, but if I have the same shape of this graph, this actually means something very different. And this is normally where people mess up on the AP Physics part, is they'll see a graph and they'll automatically assume that it's a displacement versus time graph, and they're not paying attention to what's right here. That number, or sorry, that letter is very, 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 very important because they don't actually, they'll say it in the sentence. They'll be like, attached is a velocity time graph, but most of the time whenever people are reading the instructions, they don't really pay attention to what graph they're given. And they just no, they don't even. I would actually argue that they don't even pay attention to the numbers. I would argue that they just look at the shape and they're like, okay, this is distance versus time. Okay, so whenever y'all see problems like this, please, 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 the first thing that you do is look on where the what the y-axis is. Find out if it's distance or velocity or acceleration, because those are three big different things, and the way that you think about it makes a huge difference. Okay, so let's think about this. If this is a velocity versus time graph, what is happening here? We are speeding up. Okay, that is true. What are we doing here? Yes, we are staying at a constant speed. That could be standing still, but that could also be moving at a constant speed. Because think about it. Let's say that this velocity up here, let's say that this is 20 meters per second, which is roughly about 40 miles per hour. If it's a flat line going across, that means that you are constantly going 20 meters per second. If the flat line is right on the origin, then you're standing still. You have your constant speed is 0. Okay, but right here we have our constant speed up above the part. And then down here for the third part, what's it doing? Slowing down. Okay, I will accept slowing down. Just don't say decelerate. This is it is a velocity time graph, but the slope of the line is the acceleration. Okay, and we can see that because if we know that it's rise over run, so the rise is going to be measured in meters per second, and the run is going to be in seconds. So that comes out to meters per second squared. So the slope of a velocity time graph is the acceleration. The velocity time graph can show you what the acceleration is. And you want to make sure that you do that because if you have a displacement versus time graph and there's acceleration, I'm just going to make it quick. I'm going to put D here and T here. If you have a displacement versus time graph and there's acceleration involved, it's going to do this. It's going to curve. Okay, so good luck finding the slope of that line. If you're in calculus, you can. If you're not in calculus, you're going to have to guess. So what you do instead, I don't like guessing. So what you do instead is if you have something that's curving like this, you look at the velocity time graph of it and you get the acceleration using the slope of that line is what you would normally do. Okay, because calculus is totally not a requirement for this class and they won't ask you any calculus questions. Yeah. No, they will not always give you the velocity versus time graph. If they give you the displacement versus time graph and you do not have this, we're going to have to use a different trick that I'm going to teach you later. Okay. There is a series of kinematic equations that we can use to solve. So if we don't have the velocity time graph, we can still find the acceleration of the object without having to cry. Okay. No, you'll be fine. Calculus isn't that bad. It's different, but it's not bad. Um, the algebra and the trig that goes along with the calculus is the hard part, not the actual calculus part itself, to be honest. Um, now, if you want to find, and here's where we can actually do this and it actually works, besides me being an idiot. If you want to find the total distance that was traveled, then you can calculate the area under the curve, and it will tell you the total distance that was traveled. And and here's where it works, and it is dimensionally accurate, and I'll show you that it's dimensionally accurate. So I'm going to say area under the curve, if y'all feel that you're brave enough to write it with me, that I actually got it right this time. The area under the curve is equal to the total displacement, okay? And I'm going to go ahead and just write the units out. So this is still a triangle. So let's say that it's the same thing, and this is 4 seconds. And oh, I can't be the same thing because I put 20 up there. So this is 20 meters per second going up to the top, and it's 4 seconds going across. So if we were to calculate this, this is a triangle. So the area of a triangle is going to be 1/2 the base of 4 seconds times the height of 20 meters per second. And if you look at the units that go along with it, there's seconds on top here, and there's 1/seconds over here. So you've got one on top, one on bottom. They cancel out, and your answer is going to be in just meters. So this will give you your total distance that was traveled between it. And from there, it's just regular algebra. So half of 4 is 2. 2 times 20 would be 40. So in total, that thing traveled 40 meters from one spot to the next. Okay. Another thing to consider is that even though this slope is going down, this is still going to be a positive distance that was covered because you're going positive 20 meters per second. You're traveling to the right, and then you're slowing down still in the right direction. So this displacement that occurs on the right side of the graph is going to add to the total distance even though the slope is going down. And a lot of people see that negative slope and they're like, oh, I need to take that away. You only take it away if it goes below the line itself. Okay? Does that make sense? Okay. Do I need to show y'all an example of that? You're okay? Um, Let me show you one trick. I'm not going to actually like do the math behind it, but I'll show you one trick that you can use, and it does show up once in a while. If you have a velocity time graph, so VT, and just sketch it this way. Try to make a rectangle and then try to make the same rectangle but in the opposite direction. Okay, that means that the total displacement is 0. So that means that you were going one direction and then you ended up going the opposite direction. So when you calculate your total distance, yeah, when we find the area under this curve and then you find the area under this curve, they end up being the exact same number, but they're opposite. So, say if you tried this one and you came out with like 40 meters, then this one down here is going to be negative 40 meters. And I'm just making stuff up. This is, if you calculate it and it comes out the same, if it looks the same and they have the same dimensions, you don't even have to do the math. So, like, if it's a rectangle and you looked at the sides of the rectangle and they're the same, they cancel out. Okay, so the total distance that goes between them is 0. And on an open response question, that's exactly how you can explain it. You can be like, I looked at the two shapes are on opposite sides, so they cancel out. They would give you they would look at that and be like, wow, this person really knows what they're talking about. Okay, so you don't have to do the math to get the answer right. You do have to know the concept though. So do me a favor, and if you do it that way, please say total displacement is the area under the curve. Okay, or just say is the area or something. Please say the word area in this question and like actually write it down. You have to say the word area so that they know what's going on. So like displacement equals area, they'll be like, oh, okay, this person knows what's going on. Um, don't make them guess on what you're doing. So like if you tell them what you're doing, it goes much better for you on the AP Physics test, I promise. Okay. And then the last kind of equation of motion, I do not have a whole lot of time left, do I? Okay, so I only have 3 minutes left. We'll handle it Monday, right? So like the acceleration versus time graph we'll handle on Monday. And then I have a really cool thing to show you that kind of ties it all together. And then you should be able to handle most of the stuff that we've done on those homework assignments. There may still be a couple of them that might throw you. Let me know if those happen, and we'll go ahead and we'll call it here for today. So have a good weekend, digital people.